we see here is that if you look at this low frequency cycle, which is the current, AC current at the output side, and we consider the one leg of this three-phase inverter. So during this positive cycle, if the switching is taking place between S1 and S2, and the switches of S1 and S2 have the complementary gating signal. So what happens is that during the positive cycle, the S2 is always switched under 0 voltage switching, because when this current is positive and you turn off this switch S1, then this positive current is going to go through this diode E2, turn on this MOSFET S2, and then we can turn on the IGBT. So we are doing the 0 voltage switching of this device during the positive cycle. But what happened is that when we're turning on and off this switch here, which is S1, then this S1 does not have the 0 voltage switching. So we have the hard switching for this particular cycle. So similarly, the role of S1, S2 reverses when we are going towards in the negative cycle. So what happened is that by combining the IGBT with MOSFET, we are able to take advantage of the switching performance of the MOSFET, but we are still not able to completely avoid the switching losses, particularly when we are switching at higher frequency. And these are the somewhere 60 to 100 kilowatt inverter systems where a small loss matters a lot from the loss point of view. So it's the same thing like GV is lost at least for one switch in each leg when we are basically operating this inverter. So what can we do? Is that here is the concept of combining the two bridges. Let's say we can split the 100 kilowatt inverter into two 50 kilowatts inverters. So if we do that one, we can have these two inverters, and these two inverters are connected together through the use of high frequency inverters, high frequency inductors, which are shown here. And so if we do that one, then we can avoid, or we can achieve the 0 voltage switching, and we'll see how. So what happened is that if we look at this particular diagram, so what happened is that when we are switching, let's say MOSFET in this one, then we can phase shift this MOSFET with respect to this one and generate some circulating current through these two inductors. And that circulating current now basically helps in terms of correcting the polarity of the current through the various switching. So this is the let's say this is the output current, and now we need to produce this kind of current pattern through the phase shifting of the two bridges. And this is the high frequency current, which is basically decided by the frequency of the circuit, which may be somewhere between 20 to 60 kilohertz. So now, by using some of this basic concept, it is possible to achieve the 0 voltage switching. So now what is happening is that if we go back to our previous slide where we had the full bridge inverter, so there it was the size of the capacitor, and the size of the capacitor basically and the cost of the capacitor. So even if you can tolerate the size, the cost is quite prohibitive if you want to do it. So now what we are doing is this is a trade-off between the DC capacitor and the high frequency inductors. which are basically connected between the two modules. And also what happens is the cost of two modules, which is the, let's say, 50 kilowatt versus 100 kilowatts, is not same. So the cost has to be slightly higher. But what is happening is that we work with one of the semiconductor company in US, and those semiconductor company basically they develop the power modules. So they were looking more on the concept how they can how can they simplify, okay, because for them it's more of a packaging issue. So what happens is that once you are going to the 100 kilowatt kind of power, you don't have a single device which is carrying that 100 kilowatt power. You are using the multiple semiconductor devices. So in terms of the number of devices what you are going to use, they remain more or less same. So it's just the different way of connecting them. And also what happened is that in this particular case, your gate drive circuit requirements are considerably simplified, because now we are doing the MOSFET switching, so that your gate drive circuit requirements also simplified considerably. So based on some of these things, like you still have one physically semiconductor module. So rather than it has 6 switches, it might have 12 switches, and it might have 12 MOSFETs which are assisting you in terms of the high frequency switching. But they're all semiconductor. They can be combined on one package. So you're still basically selling one semiconductor package outside. And what is happening is that now, so you have reduced the size of the capacitor, cost of the capacitor, and now what you're doing is you're using the very small high frequency inductors, which are not expensive, which are cheap, and don't take much space. So now, unlike many other sort switching techniques where we have to use a lot of auxiliary circuits, auxiliary component to achieve this 0 voltage switching. Here we are achieving this 0 voltage switching by rearranging the devices, and then we are using very small inductors on the external inductors, and they are very cheap. And so these are some of the basic control how we achieve operation. And this is some of the performance simulated performance here, and that's basically by simulation we are able to prove that we can achieve the 0 voltage switching for wide range of conditions. So that is on the DC to AC inverter. And the DC to AC inverter basically is one of the most challenging components in the electric cars, because it's generating maximum amount of heat. It's generating, let's say, for a 65 kilowatt system, so total losses are about 2.5 kilowatts. So that is a major challenge. Now we have the DC-DC converters also, and the DC-DC converters, as I mentioned earlier, is basically, let's say, DC-DC converter is somewhere between 2 to 4 kilowatts rating. But the size of this DC-DC converter is same as the size of that 65 to 100 kilowatts inverter. So what happens is that the cost of this DC-DC converter is not very different than the cost of the 65 kilowatt inverter. It is lower, but it's not significantly different. So now what happens is that if you want to reduce the overall cost of the system, so we must try to concentrate on developing the new DC-DC converters also. And also there are some other requirements from the control side for the DC-DC converters. So if we really look at, we are having a 300 volt DC bus, and this DC bus is going from somewhere 220 volts to 430 volts. There is quite a bit of variation here. And output is a 12 volt, because it's a low voltage bus, and we are producing somewhere between